Just looking at continuing on with the review exercises. And last time we looked into exponential equations. Okay, some that have a common exponential base, others which don't. And let's say that from the first group, okay, we have for exponential equations, and there was one remaining item that did share a common base, and that was with number 15. And we have also from the set for those exponential equations that do not share a common base, we have with numbers 20 through 24. And I'll tell you what, we'll go ahead and look into these items and then cross over to other types of equations. Okay, so we have for the case in number 15, okay, see we have 1 over 1,000 raised to the x is equal to 10 raised to the 1 plus x. Now this equation is going to have a common base, okay, with 10, okay, which we have to already appear on the right hand side of the equation, okay. And if we write what we have on the left in terms of base 10, okay, so you got the reciprocal of 1,000. And 1,000 is going to be not only a multiple of 10, but also an integer power of 10. Okay, so 1,000 would be 10 cubed, so we have the reciprocal of 1,000, okay, to be 1 over 10 cubed. So you have 1 over 1,000 to the x, so it'll be 1 over 10 cubed raised to the x. And the right hand side we already have directly in terms of base 10. And now for what I have on the left, okay, so I have 1,000 in terms of base 10, but I want to get out of the fraction mode and put directly what I have with 1 over 10 cubed in terms of base 10, okay, without the fraction. So we have with the inverse rule, if you have the reciprocal of a base to a positive power, it is going to be the base raised to the negative of that power. Okay, so 1 over 10 cubed, okay, this is going to be 10 to the negative 3. So 1 over 10 cubed to the x, okay, we have 10 to the negative 3 raised to the x. Again, we have waiting at the right, we have 10 to the 1 plus x, and we have with the application of the power property of exponents, so a base to a power to another power would be the base to the product of those powers. In this case, we're going to have 10 to the negative 3x is equal to 10 raised to the 1 plus x. And now that we have single base 10 terms, we can now set the powers equal to each other. Okay, so you have negative 3x from the left is equal to what we have from the right with 1 plus x. And if we gather the variable terms, so we have negative 3x by itself on the left, and we have the like term with x on the right, so we can gather once again the variable terms, and here I can just take x away from both sides, and so we're going to have that negative 4x is equal to 1. And with division by negative 4, okay, we're going to have the x is equal to minus 1/4. Right. And for what we have in the case of exponential equations, okay, so 15 is a sample of an equation that shares a common base. Now, for what we have in the case of exponential equations that do not share a common base, and we have like in the group from 20 through 24. Okay, now we have in 20 from this set we have the variable on one side of the equation. Okay, and so if the variable is on one side of the equation, okay, I can create the pathway to the change of base formula along with the first logarithmic property where I have again the base a log of a to the x is equal to x. And so for 5 raised to the x plus 2, what I can do here is that I can free up x plus 2 from the power position if I take the base 5 logarithm of both sides. Okay, so if I do this, so we have the base 5 logarithm of 5 raised to the x plus 2 is equal to the base 5 logarithm of 18. Okay, so if you have an identity between the exponential and the logarithmic bases, the exponent is going to be the result. So here we have the reduction on the left-hand side to x plus 2. Again, we have x plus 2 is equal to the base 5 logarithm of 18. And what I can do, okay, since I'm looking for a numerical result, okay, so we have the base 5 logarithm of 18. I can apply the change of base formula where I can take the ratio of natural or base 10 logarithms. And for here, I'll just go with natural logarithms. So your a is at 5 and the m is at 18. And just writing what we have here. So I'm going to have the natural logarithm of 18 all over the natural logarithm of 5. And looking at what we have in the ratio. Okay, so we have the natural logarithm of 18 divided by the natural logarithm of 5. Okay, so right now we have among the digits. Okay, so you have 1.79588. And looking at solving for x. So if I take 2 away from both sides, and we're looking at, I believe, rounding to the nearest 3 decimal places. Yes. So if I take 2 away, okay, so we have a minus 0.204111. Okay, and to the nearest 3 decimal places. So our third decimal place is where the 4 is situated. And next to it we have the number 1. And so to the nearest 3 decimal places, okay, because we have no rounding up, we end up with x at negative 0.2 or just negative 0.204. Now we have in the case of the next item, okay, we're still working with the exponential base 5, okay, and we have the variable exponent to exist on one side of the equation. So like what we did with number 20, I can take the base 5 logarithm of both sides. Okay, so for what I have, once again, okay, so the basis 5 will go out. So the left-hand side, okay, we have going to x minus 1. Again, we have equal to the base 5 logarithm of 3. And for what we have numerically, for the base 5 logarithm of 3, okay, I can apply the change of base formula. And I can reapply either the natural logarithms or I can just go with the ratio of logarithms in base 10. So I'll go with the base 10 logarithmic ratio. So I have log of 3 all over log of 5. And so for what we have here, so the base 10 logarithm divided by the base 10 logarithm of 5. Okay, so we're looking at right at 0.68260. And adding 1 to both ends. Okay, so you have for x Okay, so you have 1.6826 among the first digits. And if I'm looking at rounding to the nearest 3 decimal places, okay, so you have 2 in the 3rd decimal place, and we have with 6, and since the 4th digit after the decimal point is 5 or greater, okay, this will signal that 2 is going to round up. So we have to the nearest 3 places, we have the solution for x to be at 1.683. Now, okay, so for 20 and 21, we've had the exponent on one side of the equation. Now, for what we have in the case of 22, okay, notice we have the variables, x, okay, or the variable expressions of x to be on both sides, okay, so it's not quite so automatic to create a change of base pathway like what was in 20 and 21 since we had the variable on one side. But now that we have x on both sides, we can follow through and apply this time either natural or base 10 logarithms on both sides. And say, well, we'll go with base 10 logarithm in this case, but ln would also work. Okay. Now you don't have a match between the logarithmic and exponential bases on either side, but in terms of what we can do with both x plus 1 and x minus 3, again, we can apply, okay, I believe what was our 4th property, where we had that the base a logarithm of m to the r is equal to r times, okay, the base a logarithm of m. Okay, so here we can convert the exponents to variable coefficients. So for x plus 1, I can move that in front of the base 10 log of 4, and for x minus 3, I can move that in front of the base 10 log of 18. Okay, and for this one, okay, to signify that we have all of x plus 1 multiplying the base 10 log of 4, okay, I want to use parentheses. For what I have to the right, okay, I want to use parentheses around x minus 3 since all of that statement is multiplying the base 10 log of 18. Now, looking at what we have in the next round. So we're going to be looking at distribution. Okay, so we're going to have the formation two base 4 logarithmic terms and a couple of base 10 logarithms with the base 10 log of 18. Left is going to be a couple of base 10 log of 4 terms. So we have x times the base 10 log of 4 plus the base 10 log of 4, and that's going to be equal to x times, okay, the base 10 logarithm of 18 minus 3 times the base 10 log of 18. Okay, and so we have variable terms again on the left and the right hand side of the equation. And what I can do is that I can gather the variable terms. So I have x times the base 10 log of 4 on the left, x times the base 10 logarithm of 18 on the right. And I can join these terms together. And what I will do, I'll just move the term x times the base 10 logarithm of 18 and have the variable terms on the left. And for the non-variable terms, okay, I'm just going to have those exclusively on the right. So looking at what we have in the settings here. Okay, so to the left, okay, with this approach, we have x times, okay, the base 10 logarithm of 4 minus x times, okay, the base 10 logarithm of 18. Okay, we have equal to -3 times the base 10 logarithm of 18 minus the base 10 logarithm of 4. All right, now we still have a couple of x terms, but what I can do is that I can express as a single term in x, okay, initially, okay, by factoring out x. So upon factoring, so we have x times the quantity of the base 10 logarithm of 4 minus the base 10 logarithm of 18. Again, we have equal to the same difference between -3 base 10 logarithm of 18 and the base 10 logarithm of 4. And looking at isolating x, so I'm going to have created a ratio where we have what was on the right is going to be divided by the difference between the base 10 logarithm of 4 and that of 18. And looking at setting things up, okay, whereupon I can get to the decimal approximation, okay, and if I write this as a consolidated statement, okay, so you got the numerator with two terms, okay, I'm going to do a bit of color coding, so I got -3 times the base 10 logarithm of 18 and minus the base 10 logarithm of 4. Okay, so I'm closing out for 4, and again, closing out for the difference that we have in the entire numerator. Okay, then we have divided by, and again we have two terms in the denominator, so I'm going to enclose that combined expression. Okay, so we're looking at, again, we have the base 10 logarithm of 4 minus the base 10 logarithm of 18 and looking at, okay, where we're going to have to the nearest 3 decimal places. Okay, so you have with our statement, so you have -3 times the base 10 logarithm of 18 minus the base 10 logarithm of 4. So you're closing out for 4, and then for the whole numerator, and we have divided by, again, we have the quantity, so you have the base 10 logarithm of 4 minus the base 10 logarithm of 18. And so we have, so you have among your digits, okay, so you have x is equal to 6.6 86763, and we have to nearest 3 decimal places, so we have the 6 after the 8 in the third decimal place, and alongside it is 7, so this 6 is going to round up, so we have to the nearest 3 decimal places for x, and we come out to 6.687. Right. Now, for what we have in the case of the next items, okay, and we have with number 23 and 24, okay, and in this one, okay, so you have the variable expression on one side of the equation, so you have e to the x plus 1 is equal to 14. And for what we have here, okay, so I can create the change of base formula pathway. Okay, and if I go ahead and take the base C logarithm of both sides, so the base C logarithm of e to the x plus 1 is equal to the base C logarithm of 14. Okay, so you have base C exponential base e, so that's going to go to x plus 1. Again, base C logarithm of 14, we can go ahead and arrive at that result because the base C logarithm is a natural logarithm. Now for the natural logarithm of 14, okay, so you have 2.63905, okay. And then looking at solving for x, so if I take 1 away, and looking at rounding to the nearest 3 decimal place, say 9 is in the 3rd decimal place, 0 signals that the 9 remains fixed. And so to the nearest 3 decimal places, we have for x, this is going to end up at 1.639. All right, now for what we have in the case of 24, okay, now we got e to the x minus 2 is equal to 3 to the x plus 1. In this case, you can either apply natural or base 10 logarithms on both sides, okay? And if you went with natural logarithms, okay, since you had the base e, it might at most save you half a step. But I tell you what, we'll go with base 10 logarithm. But it doesn't matter which one you use. Let's go with log on this one. Okay, and we have for this statement, okay, again, we have for the variable expressions, we can rewrite these as variable expression coefficients. Okay. Again, so with x minus 2 and x plus 1 rewritten as coefficients, so left-hand side, okay, we'll have all of x minus 2 times the base 10 logarithm of e is equal to all of x plus 1 times the base 10 logarithm of 3. Okay, and then looking at expanding on the left, we have x times the base 10 logarithm of e minus 2 times the base 10 log of e. To the right, and we have x times the base 10 log of 3 plus the base 10 logarithm of 3 and we're back in a situation, okay, where we can gather our variable terms, okay, which we have as logarithmic expressions. Okay, so I can just move x times the base 10 log of 3 had the variable terms on the left, and on the right would be the non-variable terms. Now I had this accomplished upon adding 2 times the base 10 log of e to both sides. And getting things squared away. Okay, so we're down to where we have x times the base 10 logarithm of e minus x times the base 10 logarithm of 3 is equal to the sum of the base 10 logarithm of 3 and 2 times the base 10 logarithm of e. All right. And once again, so we have a couple of x terms, and I can make it as one x expression. Okay, as I factor out x from the terms on the left. So here I'm going to have x times the quantity. So you have the base 10 log of e minus the base 10 log of 3 is equal to the sum of the base 10 logarithm of 3 plus 2 times, okay, the base 10 logarithm of e. Okay, and getting x by itself. And we have by division. So we're looking at establishing the quotient, whereupon we had the base 10 logarithm of 3 plus 2 times the base 10 logarithm of e. It's going to be divided by the difference between the base 10 logarithm of e and that of 3. And just looking at consolidating. Okay, so you have two terms in the numerator, and if I put together as a single expression, so we'll have the quantity, so the base 10 logarithm of 3 and we have plus 2 times, okay, the base 10 logarithm of e. So closing out for the numerator, I have divided by, and then quantifying what we have in the denominator. So again, we have the base 10 logarithm of e minus the base 10 logarithm of 3 and upon looking at what we have now, okay, so you have the base 10 logarithm of 3 plus 2 times the base 10 logarithm of e. You have divided by, again, the base 10 logarithm of e minus base 10 logarithm of 3 okay, so you have with the numbers, okay, so you have x at negative 31.42217 and so on. And we have with the third decimal place, this will be this 2, and since I have only 1 to the right of it, okay, this 2 will remain as it is. Okay, so you have to the nearest 3 decimal places, we have x at negative 31.422. Okay, and for what we have in the case of exponential equations, okay, and we have with the other set, okay, and we have with numbers 11 through 13. Okay, so we have with 11, so we have the base 2 raised to the x is equal to 3. Again, just kind of a basic example here, something you can anticipate. Say we have, say 2 to the first is equal to 2. And we have 2 squared is equal to 4. But somewhere in between, we have 2 to the 1 point something is equal to 3. And looking at finding out what x will be to the nearest 3 decimal places, okay, I can take the base 2 logarithm on both sides since I have only the variable x on the left. Just had the base 2 logarithm of 2 to the x. So this is going to go to x. Again, we have x is equal to the base 2 logarithm of 3. And again, I can establish either a natural or base 10 logarithmic ratio. And here I'll just go with natural logs. Okay, so I can say I have the ln of 3 all over the natural logarithm of 2 and for ln of 3 divided by the natural logarithm of 2 and we have 4 is in the third decimal place, and since it is alongside 9, that means we can round up the 4, whereupon we have to the nearest 3 decimal places, we have the value of x in this case to be at 1.585. And for what we have in the case of number 12, okay, this time we have a to the x minus 2 is equal to 14. Okay, so I have the variable expression in x on one side, so I can just apply, once again, taking the logarithmic base that matches the exponential base to the variable power. So we're back to the base c logarithm of 14. Left hand side again we have to become x minus 2. And base c logarithm of 14, again, that is natural logarithm of 14. And we had encountered natural logarithm of 14 earlier. And again, that was 2.639. And upon adding 2 to both sides, okay, so you have for x among the first digits, you have 4.639057, and we have 9 at the third decimal place, and we have only 0 to the right, so the 9 is going to stay. So it's not going to go up to the next place and carry over to what we have with 3. So in this case, instead of going up to 4.64, this will stay locked in at 4.639. Now, for what we have in the case of 13, okay, this time we have 10 raised to the 3x plus 1 is equal to 12 raised to the x minus 1 degree. Okay, and again, you could take either natural or base 10 logarithms on both sides. Now we'll just take the base 10 logarithm. So just take log. Okay, so log, okay, that's going to be a base 10 logarithm. And since this happens to match with the exponential base on the left, okay, left hand side, okay, I can go ahead and write this as 3x plus 1. And to the right, now for x minus 1, we're going from exponent to coefficient. So right hand side is going to be the quantity of x minus 1 times the base 10 logarithm of 12. Alright, so right now we've got the left hand side, no logarithmic terms. So we have 3x plus 1 is going to be equal to x times the base 10 logarithm of 12 minus the base 10 logarithm of 12 and looking at combining our variable expressions. So you have 3x to the left, x base 10 logarithm of 12 on the right. Now just move the x base 10 log of 12 I can move the 1 over. So for what we have in x, okay, so we have 3x minus x times, okay, the base 10 logarithm of 12 is equal to minus the base 10 logarithm of 12 minus 1. And this time around, okay, we have on the left, we have our x terms, and so we have two x terms that I can make into one x expression. So once again, factoring out x, we have the left-hand side is going to be x times the quantity of 3 minus, okay, the base 10 logarithm of 12 again, we have equal to minus the base 10 logarithm of 12 followed by the subtraction of 1. Okay, and so writing with x isolated, so I can divide by the difference between 3 and the base 10 logarithm of 12. And looking at calculating, so I have two terms in the numerator. Okay, and if I write in consolidated terms, so we have the negative, so I have the quantity of the negative of the base 10 logarithm of 12. Okay, then we have minus 1. Then close out for the numerator. We have divided by, okay, we have the quantity of 3 minus, okay, the base 10 logarithm of 12. So again, close out for 12 and close out for the denominator. So what we have in the numerator, got the negative of the base 10 logarithm of 12 minus 1. And we have divided by the quantity of 3 minus the base 10 logarithm of 12. Okay, so you have x at negative 1.0824445. And again, if I'm rounding to the nearest 3 decimal places, okay, so got 2, and with the 4 alongside it, so the 2 is going to remain. So to the nearest 3 decimal places in this problem, we have x to be right at negative 1.082. All right, now for what we're going to be looking into for the next portion, okay, we're going to have encountering, okay, logarithmic equations. And just to kind of give you a backdrop to this, Okay, so you have for logarithmic equations. Okay, so a bit of a prelude to this. Now we've had our various properties of logarithms. Okay, whereupon we've had the base A logarithm of a to the x is equal to x. And in logarithmic equations, now a while back when I introduced the second property, I said it might be a while before we encountered this, and we will probably not see it again until we officially got into the logarithmic equations. And again, you still have a match in this layout between the exponential and the logarithmic basis, where we have also that a raised to the base A logarithm of x is equal to x. And again, we have our change of base formula. And again, when we looked at the lead into sums and differences of logarithms, especially where part of it is converting exponents to coefficients. Again, if you don't have a match, like you have base A logarithm of m to the r, again, we can rewrite this as r times the base A logarithm of m. And also key to logarithmic equations will be our sum and difference properties. And also in the mix, when we first looked at a logarithm as the inverse of a one-to-one function, where the outcome was the inverse function, or y, was equal to the base A logarithm of x. Okay, we had that the logarithmic base, like the exponential base, was positive with the exception of 1, and the attachment that we have in the logarithmic term had to be positive. Okay, and for what we have as cases of logarithmic equations, and give you a sort of an intro to what we have here. Okay, so if I'm looking at, let's say, solving for x, we'll say we have, first of all, if I have, say I have base 3 logarithm of x plus 5 is equal to the base 3 logarithm. And so we have 2x plus 2. Now, on the basis of what we have with our properties, okay, so again, just to kind of mention, okay, whenever I had that y, is equal to the base A logarithm of x, and especially where x, the attachment, has to be positive. Okay, now this is going to signal, at least for this part. Okay, now for these terms, we have the attachment not at x, but at x plus 5 and 2x plus 2. But for these to be legitimate base 3 logarithmic terms, the attachments had to be positive. So x, whatever I get for x, x plus 5 has to be greater than 0. And also whatever I get for x, 2x plus 2 also must be positive. Okay, now we have single base 3 logarithmic terms. And now what I can do is just have one-to-one terms, like that, like for exponential equations that have identical bases, single terms, just like I could go ahead and set the powers equal to each other. Well, here I can go ahead and set the attachments equal to each other. So we have x plus 5 is equal to 2x plus 2. Now looking at solving for x. So I have x plus 5 equal to 2x plus 2. What I can do here, I'll just move that x from the left and have the variable terms on the right. And I can also subtract 2. And we have 5 minus 2 is going to be at 3. 2x minus x is equal to x. So we have an apparent solution with x equal to 3. And if I go back, okay, so 3 plus 5 is 8. It's positive. And 2 times 3 is 6 plus 2 is also 8. So we have the attachments equal to each other. and x plus 5 and 2x plus 2 with x at 3. Okay, we have both to be at 8 and are positive, so x equals 3 checks out, and so that will be the solution for this particular logarithmic equation. All right, now, and let's say that if we have the base 2 logarithm of the quantity of x plus 10 is equal to 4. So you have the base 2 logarithm of the quantity of x plus 10 is equal to 4. And again, whatever I get for x, I want to ensure that x plus 10 is positive. Okay. And now looking at, again, what was the second property? We have a to the base a logarithm of x is equal to x. And here I have a single base 2 logarithmic term. So I'll just go ahead and copy this. So again, I have the base 2 logarithm of the quantity of x plus 10 is equal to 4. And looking at applying the property of where we have a to the base a log of x is equal to x. Okay, so your a is going to be at 2. And guess what? I can free up x plus 10 by essentially treating both sides of the equation at this step as powers to which the exponential base 2 is going to be raised. Okay, so to get this to x plus 10, I'm going to treat the base 2 log of this expression as a power. So we're looking at 2 raised to the base 2 logarithm of the quantity of x plus 10. And guess what? I'm going to do the same thing with 4. Treat that as a power. So we have is equal to 2 to the 4th. Okay, so for what I have on the left, okay, so you have the exponential logarithmic bases will cancel. So this will become x plus 10 on the left. To the right, I have 2 to the 4th. And 2 to the 4th is equal to 16. And if x plus 10 is equal to 16, I'm going to have the x is equal to 6. I can go back and check. So we have 6 plus 10 is 16. 16 is positive. And it would turn out that base 2 logarithm of 6 plus 10 is going to be the base 2 logarithm of 16. Base 2 logarithm of 16 will be the base 2 logarithm of 2 to the 4th. And that would go back to 4. So 6 does fit the bill as a solution. So these are two introductory cases of what we have with logarithmic equations. Now, for what we have from the first group, okay, now this is intended to be a set of base 2 logarithmic terms, and there was a typo in number 14. Okay, now, in this statement, okay, we have the difference between base 2 logarithms, where we have the base 2 logarithm of the quantity of x plus 7 minus that of the quantity of x plus 1 is equal to 2. Now, we can make this expression into a single base 2 logarithmic term on the basis, once again, when we looked at combining like logarithmic base terms, we had that subtraction implied division in the case of combining as a single logarithmic term. So here we have subtraction is going to imply division. And so taking this approach, so we have the base 2 logarithm. We have in the ratio, so x plus 7 is attached to a positive base 2 logarithmic term. And so we have in consolidating, this will go in the numerator, whereas x plus 1 is part of a negative base 2 logarithmic term, and that part goes in the denominator. Okay, so now we have the base 2 logarithm of x plus 7 over x plus 1 is equal to 2. And again, we have for the base, okay, we have base 2. And so, again, applying this property, we will treat what we have in this setup as powers to which the exponential base 2 will be raised. Okay, so for what we have to the left, okay, this will come down to x plus 7 all over x plus 1, and we have to the right, we have 2 squared. And in terms of following through, okay, so if I multiply both sides by x plus 1, okay, so on the left we have x plus 1 is to cancel. And before I get too far ahead, okay, now whatever I get for x plus 7 and x plus 1, after I arrive at the apparent value or values of x, I want both x plus 7 and x plus 1 to be positive. Okay, so for what we have at this juncture, okay, so you got x plus 7 is going to be equal to 4x plus 4 Okay, so we have in this equation, okay, so I can combine the variable terms as well as separating from the constants. Okay, so you have 7 minus 4 is 3. 4x minus x becomes 3x. And we'll have with division by 3. Okay, so you have 1 is equal to x. So we'll have our apparent solution x equal to 1. Okay, and if we go back and check, so if x is 1, well, 1 plus 7 is 8. 8 is positive. 1 plus 1 is 2. 2 is also positive. Okay, and on the basis that the algebra is done correctly, okay, we had that x equals 1 is going to be the solution for what we have in number 14. All right, now for the next logarithmic equation, now we have with number 16, okay, so you have 2 times the base 4 logarithm of the quantity of x minus 2 is equal to 6. And one might wonder, okay, with the number 2, okay, can I divide that out on both sides, or do I have to treat it as an exponent? Well, the nice thing about this is that you can go ahead and divide this equation by 2. And it will have no bearing on how many potential solutions you'll have for x. And once again, just to restate, okay, whatever I get for x, I want the attachment x minus 2 to be positive. Okay, so after dividing by 2, okay, so this will come down to the base 4 logarithm of the quantity of x minus 2, and 6 divided by 2 is equal to 3. And so we're back at the juncture, okay, where we have a single base 4 logarithmic term, okay, set equal to a constant, okay, and I can take care of the base 4 logarithmic attachment, again, going with the a to the base a logarithm property. So both of these sides here I can treat as powers to which the base 4 will be raised. Okay, so for what we have on the left, okay, so this will go to x minus 2. And we have 4 cubed is going to be 4 times 4 is 16 times 4 is 64. And if x minus 2 is equal to 64, we have that x is equal to 66. And it's going back and checking. So with x at 66, 66 minus 2 is 64. And that is going to be positive. So 66 does check out. And for what we have in the mix with also in logarithmic equations, and we have with numbers 17 and 18. Okay, now we have in the case of 17, okay, so you have 7 is equal to the base 3 logarithm of the quantity of x squared plus 162. And whatever I get for x, I want to ensure that the attachment x squared plus 162 will be positive. And if I have any values of x in the real number system, the square of a negative is a positive, so any positive added to 162 is going to be positive. Okay, so we got 7 equal to the base 3 logarithm of the quantity of x squared plus 162. And I can either switch sides immediately or later. And I say, well, we'll just keep what we have for now. So using the a to the base a logarithm property, I can treat both sides as powers upon which 3 will be added. And for what I have to the left, for 3 to the 7th, I have a rather large number with 2,187. And to the right, so this time we have, again, with the property, that is a to the base a log, okay, with a at 3. So the 3 exponential and logarithmic base will cancel out. So we have x squared plus 162. So we have the variable term at x squared and if I isolate x squared, so I can go ahead and deduct 162 from both sides. Okay, so I have 2025 is equal to x squared, and I can just flip it where the x expression will be on the left. So you have x squared is equal to 2025, and then going with the square root property of equality. Okay, so I can go from x squared to x, and with this route, okay, so x is going to be plus or minus the square root of 2025. And 2025 is going to be a perfect square value. And, okay, so for x, we're going to have two apparent solutions with the additive inverses, 45 and negative 45. And guess what? Both negative and positive 45 will square out to 2025. And 2025 plus 162 will be greater than 0. So we have both of these items to check out. So for x, we will have both negative and positive 45. Now, for what we have in the case of number 18, we're looking at solving for x. Now here I have the natural logarithm of x squared minus 4x plus 4 is set equal to 0. And once again, whatever I get for x, I want the attachment x squared minus 4x plus 4 to be positive. Okay, and setting things up. Okay, now we got a natural logarithm. And you can go ahead and take the exponential base e, but just kind of laying it out. So natural logarithm is going to be a base e logarithm. And again, we have that of x squared minus 4x plus 4. We have equal to 0, and taking care of the presence of logarithmic entities. I can treat both sides as powers of which the natural logarithmic exponential base e will be raised. So for what we have on the left, okay, this will go to the trinomial x squared minus 4x plus 4 for what I have on the right, okay, we have e to the 0, and e is that 2.718 figure, and a non-zero number to the 0 power is going to be equal to 1. And so we have a quadratic equation. And if I rewrite this in standard form, okay, so as I take 1 away from both sides, we're going to have x squared minus 4x plus 3 is equal to 0. And here I have a trinomial that is factorable. And factors of 3 whose sum or difference will add up to -4. So I have both binomials to be of subtraction. So I have the quantity of x minus 1 times that of x minus 3 equal to 0. And for the x minus 1 equal to 0 part, we have an apparent solution with 1. And for the other application of the zero product property, setting x minus 3 equal to 0, so we have an apparent solution with x equal to 3. So looking at checking. So if x is 1, so you got 1 squared is 1, -4 times 1 is -4. 1 and -4 is going to be -3, but in turn, -3 plus 4 is a +1. Okay, so 1 checks out. Looking at 3. Now 3 squared is 9, -4 times 3 is -12. 9 and -12 will be -3. However, -3 plus 4 is equal to 1. So the input values of x at 1 as well as 3 will lead to the natural logarithm of 1, which will be equal to 0. So both 1 and 3 are workable. And so they're going to be the only two solutions that we have for x in the case of problem 18. All right. Now, for what we have with logarithmic terms, okay, and here we have a couple of base 3 logarithmic terms, and here we had the sum of the base 3 logarithm of x and the base 3 logarithm of the quantity of x minus 8 is equal to 2. Okay, and just looking at what we might have for x, we want to ensure that both x and x minus 8 will be positive. All right, and I can consolidate these expressions as a single base 3 logarithmic term. Again, in combining, the operation of addition is going to imply multiplication when combining as a single logarithmic term. Okay, so we have what will be the base 3 logarithm of what is going to be x times the quantity of x minus 8 is equal to 2. And I can go ahead and distribute x over x minus 8. Okay, so we have the base 3 logarithm of x squared minus 8x is equal to 2. So I have a single base 3 logarithmic term. And now with a at 3, I can treat these parts as powers to which the exponential base 3 will be raised. So for what I have on the left, okay, so the bases 3 will cancel each other. So left hand side will have x squared minus 8x is going to be equal to 3 squared, whereupon 3 squared is going to be at 9. Here we have a quadratic equation, and just putting this in standard form, we have x squared minus 8x minus 9 is equal to 0. And looking at factoring, okay, so x squared will go to x and x. And factors of 9 whose sum or difference will be on the negative side at minus 8. So we have only the addition of 1 and the subtraction of 9. And we have in the zero product property stage, okay, so if I set each of the factors to 0, so with x plus 1 equal to 0, I'm going to have x equal to negative 1. For x minus 9, setting this equal to 0, so we're going to have an apparent solution with x equal to 9. And looking at inspecting, okay, so you notice they have x at negative 1 and transferring to what we had in the original statement. Well, guess what? Negative 1 is negative, and negative 1 is less than 0 as opposed to greater than 0, and negative 1 minus 8 is negative 9, also less than 0. So negative 1 will not fit the requirements of being part of the attachment for these base 3 logarithmic terms. Now for 9, they got x is at 9, 9 is greater than 0, 9 minus 8 is 1, also greater than 0, so 9 is going to check out. So we could have had up to 2 solutions, but in terms of meeting the requirements of being legitimate logarithmic terms, okay, we have only one solution. Again, that is going to be x equal to 9. And for what we have in the realm of working with logarithmic equations, and we had from the other set, and we had left over, okay, I believe there were items 2 and 3. And let's see. Let me check here. Yes. Okay, so for items 2 and 3. Okay, so you have in this setup, okay, so you have the base 2 logarithm of the quantity of x plus 1 plus the base 2 logarithm of the quantity of x plus 3 is equal to 3. I'm just going to copy this. Oh, here we go. Okay, so for this item in number 2, so we got the sum of the base 2 log of the quantity of x plus 1 and the base 2 log of the quantity of x plus 3. Again, whatever I have for x, I want to ensure that both x plus 1 and x plus 3 will be positive. All right. So looking at what we have here, so I got the addition between these base 2 logarithmic terms, and I can go ahead and consolidate. And here we're going to have addition to imply multiplication. So the base 2 logarithm of the quantity of x plus 1 times that of x plus 3 is equal to 3. And I can go ahead and FOIL out x plus 1 and x plus 3. So you have the base 2 logarithm. Okay, what's going to be x squared plus 4x plus 3 is equal to 3. And for what I have here, so I have a single base 2 logarithmic term, and I can take care of the presence of the base 2 log by treating both sides as powers to which the exponential base 2 will be raised. So for what I have on the left, okay, so I'm going to have this to become x squared plus 4x plus 3, and to the right have 2 cubed. So that is going to go to 8. And rewriting this quadratic equation in standard form, so if I take 8 away from both sides, so we have x squared plus 4x, and what's going to be minus 5 is equal to 0. And here I have a trinomial that can be factored. So x squared will go to x and x, and factors a negative 5 whose sum or difference will be on the plus side at 4. So we have x plus 5 and x minus 1. And looking at, again, itemizing the factors and setting to 0. So we have with the zero product property, if we had the x plus 5 is equal to 0, we have an apparent solution with x equal to negative 5. And as for x minus 1, if I set this equal to 0, okay, we have our next apparent solution is going to be x is equal to 1. So looking at testing the legitimacy of these values as solutions for x. Okay, so with x at negative 5, and guess what? Negative 5 plus 1 is already negative. So this is already going to strike out. Now for x at 1, 1 plus 1 is 2, 2 is greater than 0. So the first half of the litmus test is passed. Now for the other half, got 1 plus 3 is 4, and 4 is positive, so only 1 checks out. So for this equation, in number 2 for this set, we have only x is equal to 1. Now, for what we have in the case of number 3, so here we have the difference of natural logarithmic terms. Okay, so we have the natural logarithm of the quantity of 2x minus 7 minus the natural logarithm of x. And so just looking at what we have now, okay, now before with number 2, we had addition to imply multiplication of the attachments when we consolidated. Now that we have subtraction, we're going to go in the other direction where subtraction is going to imply division. Okay, and before I combine, I want to ensure that whatever I have for x is going to result with 2x minus 7 greater than 0, and also where x is positive. And looking at combining into a single natural logarithmic term. So we have ln, okay, and with 2x minus 7 as attached to a positive natural logarithmic term, this will go to the top. And with x attached to a negative, we'll have x on the bottom. Okay, so we have natural logarithms. Okay, so again, ln is going to be a base e logarithm. And I can treat both sides here as powers to which the natural log base e will be raised. Okay, so for what I have on the left, okay, so this will be 2x minus 7 over x. And we have e to the 0 is equal to 1. And if I multiply this equation on both sides by x, so you have on the left, okay, so we have x's to go out. And we have 2x minus 7 is equal to x. Okay, so you have x by itself on the right. And if I join this with 2x upon subtracting that term on both sides, so this will come down to negative 7 is equal to negative x. And changing the signs, okay, so we have 7 is equal to x, and so we have an apparent solution with x equal to 7. And checking the legitimacy, okay, so with x at 7, we have 2 times 7 is 14. In turn, 14 minus 7 is 7, which is positive, and 7 is already positive. So as a solution for x, x equals 7 fits the bill. And again, with the natural logarithmic exponential base e, we have seen this number in various capacities. And among the elements or items, okay, we've had along the lines of business applications. And from the first set, okay, when we looked at compound interest, and let's say that for the second set, which one? I think I've got a first set left. Yeah. So you have for compound interest and future value. Okay, so you have for number 25. Okay, so we're looking at finding out the future value of $3,000. And we have different frequencies. Okay, we have part A have monthly compounding. Part B, you're looking at continuous compounding. And now, for the setup, okay, so you're looking at the future value of $3,000. Okay, and this will be applied to both parts. So you got $3,000 rate of interest. Okay, we're going to have at 10%. And to be able to do the computations, okay, again, we write the rate as a non-percent decimal value. Okay, and we're looking at the time span for 6 years. Now for the monthly compounding. Okay, so we have so you have an added variable, okay, with n equal to 12, since we have monthly compounding. and in configuring, okay, what the future value is going to be after monthly compounding. So for the future value, where we have the frequency to range from annual to daily compounding. Okay, we have the principal P times the quantity of 1 plus R over N raised to the N times T power, and with the values of P, R, T, and N available. So you got 3,000 for P. For 1 plus R over N, so R we have at 0.10. And N, okay, since that is factored in, so you got N at 12. And the degree we're going to have the product of 12 and 6, or the N times T portion. Okay, now for what we have for the sum between 1 and this ratio between 0.10 and 12. So you got 3,000, and what's going to be times 1.008. And we have repeating threes after this. And just keep that decimal. And raising this, okay, to the 72nd degree. Okay, so I have 1.08 and then repeating threes, okay, raised to the 72nd power. So I write at 1.81759. Just keep that and multiplying by 3,000. Okay, and just expressing A in terms of dollars and cents. So after 6 years of monthly compounding at a rate of 10% after a one-time investment of $3,000 is made, okay, we end up to the nearest penny at 5,452.78. So again, this is with monthly compounding. Now for part B, we're looking at continuous compounding. And with continuous compounding, okay, so you have like n is approaching infinity, and we have for what would otherwise be this formula, we had the 1 plus r over n to the n times t to converge upon e to the r times t degree. So just looking at the numbers, okay, so you have P is at 3,000. Now for e to the r times t, okay, so we have e, r we have at 0.1, and t we have for 6 years. Okay, now there doesn't seem to be as much to work with in comparison to the non-continuous future value formula, but you had to be careful with the order of operations. So we'll go ahead and take the product of r and t. Okay, so 0.10 times 6, so we have what's going to be e to the 0.6, or 0.60. And for e to the 0.6, okay, so we have 1.822. $11.88, and multiplying by 3,000. Okay, And so we have for the future value in this case. All right. And again, at the same time, rate, in terms of the quoted percentage, as well as the same initial investment, the more frequently that the compounding is done, the higher the balance will be. So for monthly, have the future value at 54.5278. Now for continuous, okay, this is going to be somewhere between $13 and $14 more, where we have that estimate at $5,466.36. Okay. Now, also where we have one-time deposits, and we have with the compounding of interest, and we have for this next group, okay, for 16 and 17. Okay, so in the layout for 16 and 17, okay, so you have, once again, we have the principal. You have a $3,000. Now the rate is going to be at 6% as opposed to 10%. And we still have the time span for 6 years. Okay, now for 16, okay, so we're looking at quarterly compounding. So in this case, we have with quarterly compound, we have that n is equal to 4. And for what we have in the setup, okay, we have all the P, R, N, and T are known. So just filling in the numbers. Okay, so for P, we have 3,000. Times the quantities, so you have 1 plus 0.06. We have over N with N at 4. And we have to the N times T power, so we have 4 times 6. Okay, now for the sum, okay, we have what's going to be 1.015. And 4 times 6, okay, we had 24. Okay, so 6 years of quarterly compounding, you have a collected total of 24 compoundings. And for 1.015 to the 24th, okay, so you have a number that is just under 1.43. And multiplying by $3,000. Okay, and so for that figure to the nearest penny, we're looking at 42.8851. As for 17, okay, still working with the same P, R, and T. And again, we have continuous compounding. And going ahead and filling in the numbers. Okay, so we have P at 3,000. for e to the r times t. So you have e to the 0.06 times 6 so 0.06 times 6 is going to be 0.36. And for what we have, again, be careful with the order of operations. Okay, so you have e to the 0.36 and for e to the 0.36, okay, so you have 1.4 3329 and multiplying by $3,000. Okay, so you have a higher balance. That's almost $4,300. Okay, but to the nearest penny. We have right at $42.99.99. Okay, so these items, okay, we had to be in reference to one-time deposits, and let me give you just as an intro to annuities. Okay, I'll show you the theoretical minimum as well as the theoretical maximum future value. Okay, let's say that for say if you have for recurring deposits made at the end of the investment cycle, okay, so if you have for recurring deposits made at the end of the investment cycle where investments are made n times a year, and interest is also compounded. In other words, the frequency of the installments and the frequency of the compoundings of interest will be the same. Okay, so we're going to have the future value is going to be, and this will look like an augmented version of the non-continuous future value formula. And in one sense, it is. Okay, so you have for A, then we have P times, then we have times the quantity. We have of the quantity of 1 plus R over N raised to N times T. But this time we're going to have, in addition, we have minus 1, and then we have times N over R. And this is going to be for recurring deposits. Now, this is going to be the minimum, theoretically minimum total at the end of the cycle, and also for the investment time period. Okay, but let's say that for what we have at the maximum. Okay, say if you have, like for recurring deposits, instead of being made at the end, instead of at the end, we have to be at the start. Okay, you're going to have the future value is going to be this, but it's going to be times one more added detail. You have your theoretically minimum future value amount. Okay, but at the start, okay, so this is signal that we'll have just like an added ingredient that's going to max out the total, and this will be multiplying by the quantity of 1 plus R over N. Just that part, okay, is going to make that difference between the theoretically maximum and the theoretically minimum amount. And for what we have in the case of taking what we have with annuities, and we have from what we have from the first set with annuities, okay, and we have Ray, who has a plan to retire, okay, and he's looking at 15 years down the horizon, and his approach is to contribute $1,000 to an IRA on a semi-annual basis. And if you notice, we have the rate of return to be compounded, okay, where we're going to have it 10%, and you have the frequency also is going to be on a semi-annual basis. Okay, so we have just laying the groundwork. Okay, so we're looking at part A, what would be the minimum value, as well as what would be the maximum value, and just some things to mention. Okay, and we have first of all, okay, we have the key items. Okay, so he is regularly contributing $1,000. Okay, so P is at $1,000. Okay, and we're looking at semi-annual, both the compounding of interest and the frequency of the contributions. So N is going to be equal to 2. And again, he plans to retire in 15 years. So go ahead and say that. Okay, so we got T is equal to 15. And for what we have for the rate of interest, okay, so we have R is going to be at 10%. So we have at 0.10. Okay, so looking at what we have for part A, okay, so inserting the traditional annuity formula. Okay, that considers the minimum side of the future value. Okay, so we got our quantities P, R, N, and T already established. Okay, so we have with P, again, we have 1,000. You know, times the quantity, so for 1 plus R over N. So 0.10. Okay, N is going to be at 2. And then we have to the N times T, so that's going to be 2 times 15. So the power is going to be at 30. and we have minus 1. Now for times n over r, n we have at 2, r we have at 0.10. Okay, so the only thing I've done is substitute the numbers for the letters. Okay, now for what we have in the activity, so you got $1,000, the principal. Now we have for the sum, okay, so that's going to be 1.05. And for the power, you got n times t, 2 times 15, so that is going to be 30. Okay, so got 1.05 to the 30th minus 1. Then you have 2 over 0.10, so that is going to be at 20. Now for 1.05 to the 30th, okay, so you have a number that is slightly over 4.3. So 4.3219 something, take away 1, you have times 20. And taking away 1. So we have 1,000. And for your difference, okay, I'm just going to write out all the digits. Say I have 3.3219. 42375. Times 20. And for the minimum value of the IRA, okay, putting this in terms of dollars and change. Okay, so we're looking right at 66,000. $438.85. Okay, now for what we have in the case of Part B, okay, we're looking at what would be the maximum value of the IRA when Ray retires. Okay, that is if he had invested at the start as opposed to the end of each 6-month cycle. So Part A is where we had the investment at the end of each 6-month cycle. That is for the semi-annual periods, you have 66,438.85. Now for what we have in the case of Part B, okay, remember, you got the annuity formula, but with the max, okay, you're looking at the annuity formula times 1 plus R over N. So I could just take all this information from Part A and can just multiply by 1 plus R over N. Okay, so for 1 plus R over N, so R will have a 0.10. And N we have at 2. Okay, so I have 66,438.85 times 1.05. Okay, so there's going to be like a 5% bump. Okay, and so we want to have, for the theoretically maximum, okay, we're looking right at $69,760.79. And again, just kind of doing some comparing and contrasting. And we have with the other annuity situation, this is from the second part. So we have another 15-year plan. Okay, $1,000 is contributed. And this time we're going to have for the non-continuous compounding, we're looking at, for non-continuous compounding case, so we have, instead of semi-annual compounding, we're looking at where the compounding and the installments will be on a quarterly basis. Okay, so we have for this part, okay, so we had that P, okay, we have equal to $1,000. And we have the rate of return again is going to be at 10%. And we have the N is equal to 4 this time around. And we're looking at the time period also for 15 years. Okay. And there's going to be, the numbers look the same, but with the change up from semi-annual to quarterly, okay, there's going to be quite a difference between the balances, okay, from what we have with the semi-annual and what we're going to have with the quarterly. So we have for this part A, okay, just for the, say we have the installment, the theoretical minimum, we have the installments are made at the end of each quarter. So you have with the numbers, okay, so you have 1,000 for P. And for times quantity, 1 plus R over N. So it's going to be 1 plus 0.10. Instead of over 2, and we have over 4. And for N times T, instead of 2 times 15, it is now going to be 4 times 15. Then we have minus N, or say minus 1. Okay, then we have times N over R. So N we have at 4. R we have at 0.1. So now we've got 1,000. For 0.10 over 4 added to 1, so that's going to be a 1.025. 4 times 15 is 60. And for N over R, I have 4 over 0.10. Okay, so this will be 40. Okay, now in comparison to the semi-annual, okay, now we've got a smaller sum but a larger power. Before we had 1.05 to the 30th, now we got 1.025 to the 60th. And for this number, okay, so we have 4.399 something, take away 1. Yeah, for the difference, say, so we're going to have 1,000 times, okay, and we have for the difference inside the bracket, so you have 3.399. $789,749. Okay, and multiplying by both 1,000 and 40. So the minimum future value in this case will be $135,991.59. And for what we have in the case of Part B, okay, if investments were made at the beginning of each quarter, every quarter, okay, for the 15-year time span, that is looking at the theoretical maximum okay, so again we have 135, 991, 59, and again had that number multiplied by 1 plus r over n. And for 1 plus r over n, so that's going to be 1.025. And so for the theoretical maximum balance, okay, so we're looking at $139,391.38. All right, now just some quick things. Okay, now there is going to be a set of remaining portions that we're going to have with the equations. Okay, but I just want to go ahead and look at the added test 4 review items, and just looking at this part for looking at evaluating expressions. Okay, and for this particular set in part A, so you had the base 6 logarithm of 6. Okay, and if you notice, we have a match between the exponential and the logarithmic base. Okay, so base 6 logarithm of 6 I'm being redundant here, but you had the base 6 logarithm of 6 to the first. And that is going to be equal to 1. Now, for what we have in the case of Part B, so the base 4 logarithm of 1 over 64 Now 64 is both a multiple and an integer power of 4. But now we got 1/64. Now 64 is going to be 4 to the third. 1/64 is going to be 1 over 4 cubed. And if I rewrite what I have here in direct exponential base terms, 1 over 4 cubed is going to be 4 to the negative 3 and for this outcome, okay, that is going to end up as minus 3. Okay, so the base 4 logarithm of 1 over 64, that is equal to negative 3. And also for evaluating expressions, okay, so we have with Part A, so we have with the base 5 logarithm of 25. And go ahead and reduce. Now 25 is both a multiple and an integer power of 5. So the base 5 logarithm of 25 is going to be the base 5 logarithm of 5 squared. And so that will go to 2. And for what we have in Part B, so you have a base 2 logarithm of 1 over 32. And just as 64 is both a multiple and an integer power of 4, you have 32 to be with the same respect to 2. So here we have the base 2 logarithm. Now for 32, 32 is going to be 2 to the 5th. So 1 over 32 will be 1 over 2 to the 5th. And rewriting directly in terms of base 2. So we have 1 over 2 to the 5th is going to be 2 raised to the negative 5 on the basis of the inverse rule. So now we have, in the rewrite, we have a match between the exponential and the logarithmic bases. And so we have with the outcome, this will wind up at minus 5. And for what we have in the case of expressions, okay, just for evaluating. So after the base 8 logarithm of 1/8, you say I had the base 8 logarithm, okay, you have the denominator already consists of 8, and you can write this as 1 over 8 to the first. And in direct terms, 1/8 or 1 over 8 to the first is going to be 8 to the negative 1. And now we have the base 8 logarithm of 8 to the negative 1, and that will go to minus 1. And probably out of the set for the base 3 logarithm of 81. Okay, so we have 81 is going to be both a multiple and an integer power of 3. So for 81, okay, 81 is going to be 3 raised to the 4th. So yeah, 3 times 3 is 9, times 3 is 27, 27 times 3 is 81. So we have in terms of base 3, we have a match where the exponential logarithm bases will cancel, and the result is going to be the power of 4. All right. Now, for what we have in terms of evaluating, and it's kind of going back to sums and differences of logarithmic terms. So you have, in this case, you have a base 9 log of 7 plus a base 9 logarithm of 10. And what I can do here, okay, so we got addition to imply multiplication. So this is going to be the base 9 logarithm of 7 times 10. And so for the missing value to fill in inside the box, okay, we're going to have the number 70. So the outcome here for the base 9 log of 7 plus that of 10, we have the base 9 logarithm of 70. Okay. All right, and for what we have in the case of the base 4 logarithm of the missing value minus the base 4 logarithm of 5 is equal to the base 4 log of 3/5. You can do this in either way, and for some of you it might be strongly implicit, okay, what the value is going to be since we have subtraction to imply division. I'll just kind of present it in this fashion. So you had the base 4 logarithm of x minus the base 4 logarithm of 5 is equal to the base 4 logarithm of 3/5. And if I continue to add the base 4 logarithm of x minus the base 4 logarithm of 5, and again, we have subtraction. If we consolidate, this will come down to the ratio whereupon we have the base 4 logarithm of x over 5 is equal to the base 4 logarithm of 3/5. And guess what? So we have single base 4 logarithmic terms. And I can just set x over 5 equal to 3/5. Well, guess what? X over 5 equal to 3 over 5. So we're going to have that x is equal to 3. Okay. So again, we have with these amounts. Okay, so in part A, okay, we have 70. We have the base 4 logarithm of 3. And for what we have in part C, okay, now 25 is neither a multiple nor an integer power of 6. But if I rewrite where I had the attachment to be transformed from 25 to 5 in spite of being in a base 6 logarithm. Okay, what I can do here is that for 25 relative to 5, okay, now 25 is going to be 5 to the second. And if I rewrite going from degree to coefficient, it's going to turn out that for the base 6 logarithm of 25, so we're going to have the base 6 logarithm of 5 squared. And so we're going to have converting from exponent to coefficient, we're going to have 2 times the base 6 logarithm of 5. Okay, so that missing value would be, in this case, 2. We have 2 times the base 6 logarithm of 5. And let's say just kind of rounding out what we have for expanding. Okay, so here we have the log, in this case base 10 logarithm of z times y to the 9th. And okay, so if I write this, okay, where the expression is not going to have any exponents, so looking at expanding, okay, all right, so again, the factors, we have multiplication, and in the case of expansion, okay, multiplication will imply addition. So we'll be looking at adding logarithmic terms in base 10. So you have log of z plus log of y to the 9th. And again, just going from exponent to coefficient. And we have for the end result here, we'll have the base 10 logarithm of z plus 9 times the base 10 logarithm of y. And in the case of looking at also expanding, so we have what's going to be the base 10 logarithm of z cubed over the square root of x to the 5th times y. And kind of like in the earlier exercises when expanding, okay, so if I'm looking at radicals, I can rewrite as non-integer exponents. And we have in the denominator, okay, so we have the square root of x to the 5th times y Just give you kind of an intro here. So square root of x to the fifth times y. So the square root of x to the fifth times the square root of y. And again, for square roots, okay, we have implicitly the index numbers to be at 2. And so for the square root of x to the fifth, so that's going to be x to the 5 halves. And the square root of y, that's going to be y to the 1 half. Okay, so for this term, setting up the stage, we're setting the stage for expanding. Okay, so converting the radical to non-integer, what we have in x and y. So we have z to the third all over x to the 5 halves times y to the 1 half. Okay, and looking at drawing out and separating the terms. So we have z cubed, only factor that is in the numerator, and this is going to be a positive base 10 logarithmic term. So you have the base 10 log of z to the third, and with x to the 5 halves, y to the 1 half in the denominator. Okay, individually, these will be negative base 10 logarithmic terms. And for the result here, okay, just going from exponent to coefficient. For the base 10 logarithm of z to the third, okay, so we have 3 times the base 10 logarithm of z minus what's going to be 5 halves of the base 10 logarithm of x. Then we have minus 1 half of the base 10 logarithm of y. And this will be the result of what we have upon expanding. Okay, and okay, now for number 7 in this one case, so we have base 10 logarithm, and we have 6 times the square of the quantity of x plus 5 all over the cubic root of x to the fourth. Okay, and so for what I have in this case, just go ahead and write this. So I have 6 times the square of x plus 5. Now for the cubic root of x to the fourth, so we'll have x to the 4 thirds. I'm just going to take this out. Okay, so looking at expanding, okay, so we have 6 and the square of x plus 5 will be at the top. So the base 10 log of 6 plus the base 10 logarithm of the square of x plus 5 and then we have from the denominator we have x to the 4 thirds, and again as its own base 10 logarithmic term, okay, we have that to be subtracted. And going from exponents to coefficients, okay, now first term we have just base 10 log of 6, so there's no reduction here since 6 is not an integer power of 10. So we have the base 10 logarithm of 6. Next term, okay, the power 2 goes to a coefficient. So I have 2 times the base 10 logarithm the quantity of x plus 5. And then we have minus 4/3 of the base 10 logarithm of x. All right, and looking at expanding. Okay, so we have for number 8. Okay, so we're looking at consolidating. Okay, so we have 3 times the base 2 logarithm of w. We have minus 1/5 the base 2 logarithm of y plus 4 times the base 2 logarithm of x. Okay, now looking at consolidating. Okay, so we're going to go from coefficient to exponent. So 3 times the base 2 logarithm of w. So that's going to be the base 2 logarithm of w to the third. And we have minus, okay, for 1/5 that will be an exponent. So we have minus the base 2 logarithm of y to the 1/5. And we have for 4 base 2 log of x, that's going to be plus the base 2 logarithm of x to the 4th. Okay, so I have the coefficients moved, and now I can consolidate as a single base 2 logarithmic term. So for what we're going to have in this one, we'll have the base 2 logarithm okay, so w to the third. Okay, since this comes from a positive base 10 logarithmic term, this will be situated in the numerator. Y to the 1/5 comes from a negative term, so y to the 1/5 will be in the denominator. And x to the 4th comes from a positive, so we have this at the top. So your final result, we can have the base 2 logarithm of w cubed x to the 4th all over y to the 1/5. And we can also express as the base 2 logarithm of w cubed x to the 4th all over the 5th root of y. And just remaining item here, I'll let number 9 be the last. Okay, so if we let what we have in this particular case, now we're looking at solving for x, and 9 is kind of an interesting situation here. Okay, now we've got the base 9 logarithm of x. Is equal to negative 2. Okay, and looking at solving for x. Okay, so kind of like the requirements here. Anything in the attachment must be positive. Okay, so we got the base 9 logarithm of x is equal to negative 2. Okay, and again, I'm looking at solving for x, and what I can do is that I can take care of the appearance of the base 9 logarithm, okay, by, again, the a to the base a log of x is equal to x. So for what I have here, I can treat both sides as powers, to which the exponential base 9 is going to be raised. So you got 9 to the base 9 log of x that will go to x. I know that, like in the case of Alex, okay, like typically it's going to want you to specify, okay, just what 9 to the negative 2 is going to be. So if I had to specify, now we got 9 to the negative 2. And with the inverse rule, now 9 to the negative 2 is going to be 1 over 9 to the positive 2, or 1 over 9 squared. And guess what? 9 squared is going to be 81. So 9 squared is 81. 9 to the negative 2 is going to be 1 over 9 squared. So for x, this is going to land at 1 over 81. And 1 over 81 is going to be a small positive number, but still a value that is greater than 0.